a secant line is a line that goes through any 2 points on a graph. So say I wanted to approximate the slope at 2. I could draw a secant line between 2 and 3, and then draw that out. Would you agree that this line is kind of almost the same slope as the parabola at x equals 2? Not quite. It's really the average slope of all these points between t equals 2 and 3. But, it's kind of close. So for our purposes, it'll work. So if I was to find, now I can use my algebra 1 method of delta x over delta y here. Delta y over delta x. This is delta y, delta x. So I can do that and then find the slope from that. I'm not going to actually do it because I think you guys could do that. And to make the process more accurate, I could take points that are closer to each other and then find that secant line. And this secant line, which had 2 points closer to each other, this delta x and this delta y, will better represent what the slope is actually like here. It's going to be closer to that. And then I could take 2 points really, really, really close to each other. For example, that one and that one. You can't even see the difference there. But if you had a microscope or something, zoom in, you could see it. And then take that delta x and that delta y, the slope is going to be even more accurate. And then what we're essentially doing is drawing secant lines between 2 points that gets the points that the secant line intersects the parabola at get closer and closer and closer and closer and closer until they are infinitesimally small. And infinitesimally means like at infinity. So until they basically are just a point. Like not 2 points, they basically intersect as points. And that's the concept. Infinitesimally small. And when we get that small, we no longer have a secant line, we have a tangent line. And a tangent line is the line that intersects a graph at only 1 point. So eventually we're going to get a tangent line at x equal 2. So I'm going to draw that tangent line right there. And then if we can find the slope of that tangent line, then we effectively find the slope at that point. So to find the slope of this tangent line, I'm just going to approximate. I'm going to circle 2 points on the tangent line, and then I'm going to find the slope. So slope by delta y, delta x. So this delta y is 1, 2, 3, 4, 5, 6, 7, 8. But since it's in units of 10, it's 80. So I'm going to say m equals 80, and then delta x is 1, 2, 3, 4, 5, 6, 7, 8. Oh my. And those are in quarters, so 80 over 2, which equals 40. So that's a pretty dramatic slope. 80 over 2. But yeah, that looks right. So 40. That is the slope at 2. And I found that by doing tangent lines. Okay, so what's the slope at 3? I would draw a different color. How about a tangent line? Well, that's pretty good. Find 2 points on the tangent line. Lots of points. And then do that delta x, delta y. Delta y is 1, 2, 3, 4, 5, 6, 7, 8 times 10, 80. And then delta x is 1, 2, 3, 4. But since it's quarter, it's 4 times a quarter, which is 1. So the slope there is 80. And then the slope at 1, how about slope at 0 actually? Well, if it's parabola, it's going to go back like that. So slope of 0 is actually, like the tangent line is actually horizontal right there. So I could take any 2 points, I know the slope is going to be 0. And then the slope at 1, draw a tangent line. So I'm literally drawing tangent lines here and then trying to figure out the slope of the tangent line. It's not, it's nothing super high math. I'm just drawing stuff and then finding the slope. So 1, 2, 3, 4, 5. That's 5 up. So it's 50 up, and then 1, 2, 3, 4, 5, 6, 7, 8 over times a quarter is 2. So the slope at 1 is 50 divided by 2, which equals 25. All right. So I'm going to plot these points that we just found by using this tangent line method. down here on this graph, because the slope of the distance versus time graph, or the derivative of the distance versus time graph, is the velocity versus time graph. So, 10, 20, 30, 40, 50, 60, 70, 80. Let's just do it like that, because 80 is the highest we got. 80, 70, 60, 50, 40, 10, 0. So at t equals 0, the slope was 0, and that was green, so I'll do green. So the velocity here is 0. At t equals 1, what was it? It was red, so it's 25. 1 is 25. You know, I'm just graphing time 1, speed 25, velocity 25. At 2, it was, this was 40. Yeah, remember we did that. Could have been more neat here. I hope it's not a problem for you guys. 2 is 40. 3 was 80. Right? Yeah. And that was green. So 3 was 80. So these points represent the velocity of the robot at different times. And I could take a ton of tangent lines. You know, I could do one at every quarter and then plot every quarter. It'd probably look something like this. Okay? And if you took like an infinite amount of tangent lines, then you would get a, you know, a curve that's solid. You know, so you may notice right here that this is actually a straight line. It doesn't look perfectly straight because I drew it, but this is pretty much a straight line. Unlike the, or I don't know where it was. Oh, here it is. Unlike the jumpy thing that we had before. And it was jumpy because, you know, the robot like instantly stopped and then instantly sped up. It didn't, you know, it wasn't really realistic. Like a robot can't instantly stop. It has to take at least a little bit, you know, a few milliseconds to stop. But because this was like continuous, it's always speeding up. This graph, the speed graph, was always continuous. Okay? So if, like, hopefully now, if I give you any graph, like if I gave you a graph like this, I don't know, and I said this was the distance versus times graph, and then asked you to do the velocity versus times graph in yards per second, hopefully you could do that. And you just do that by drawing tangent lines. And then, oh, that wasn't a tangent line. Tangent line. And then taking the slopes of those tangent lines, saying, okay, the slope at time of 1 or whatever is 5, and then graphing all the slopes down here. Okay, and in doing this, we are going from one graph, taking it the derivative, and graphing it down here. All right, so I'm going to finish it up here. Today you learned, let's see, you learned what a derivative is. So derivative equals instantaneous slopes. Let's call it instant slopes. You learned that the derivative of a distance graph is a velocity graph. And that makes sense because the units, like if you just think of the units, the slope here of, you know, the slope of anything would be yards, delta y, delta yards, over delta x, which is delta t, or delta seconds. So the slope of any point in here is going to be yards per second. And then when you're graphing the slope down here, it's yards per second. You know, if this was meters, it'd be meters per second. It's pretty easy. So actually, I should tell you some notation. Here, I'm going to call distance graph is x of t. I was calling it x earlier. Let's call it f of t, x of t. And then the velocity equals, actually, let's call it d of t for now. It'll be easier. D of t, distance, makes sense. And then velocity graph. So you learn that the derivative of the distance graph is the velocity graph because of units. The way we note that, or today, there's like several ways to note that, but I'm just going to d prime of t. And prime means the derivative of it. So d prime of t equals v of t. The derivative of displacement, or distance, I'm sorry, derivative of distance is velocity. All right? And calculus, like how I just explained, is not restricted to distance and velocity. You can apply this slope finding method to just about anything. You could have a graph of force versus time, or distance in the x direction versus distance in the x or y direction, or you know, there are no restrictions to what you can apply this derivative process to. Okay, it was just velocity is the example that I use because it's kind of easiest to understand. So in our programming, in our calculations, most of the time we'll be using other units. Okay, so you know, force and time, or the speed of the left wheels with respect to the speed of the right wheels, or something like that. There's a lot of things we could do with this, and there's going to be a lot more that you need to learn before you can actually like really apply calculus in equations. But I hope you enjoyed this. I'll figure out some practice problems for you. They'll probably be easy, just graphing stuff. But yeah.